losing my voice. It's not easy to say anything. But let's continue the discussion about the semiconductors. And today we are going to talk about the extrinsic semiconductor. Extrinsic semiconductor. And let me confirm that we are going to have a final exam on the December 13th, right? Is that Wednesday? Okay. Final. You can take time about 2 hours. An open book, open note, open internet, whatever, but no discussion. No discussion. But you can use any materials that you bring, okay? And everything has to be written in English, except your name. You can write down your name in Korean, if you are Korean, right? I don't see any foreign student here. Okay, the extrinsic semiconductor. Then let's talk about the donors first. Donors. For the donors, in a flat band diagram, we can write down the conduction band and the valence band, and we can locate the donor energy level like this, okay? And the distance, we can write down ED, something like this, all right? So ED is EC minus ED, okay? And let's say ND, number of electrons at donor level, which is ED. And ND, total density of donors. You have to notice that when you say ND, that is the density of electrons at the donor levels. And as I mentioned in the last lecture, when donor is ionized, then this electron is going to go to the conduction band, so that actually the number of free carriers from the donors is going to be ND minus ND, right? That is the number of free carriers which has been here. So actually the number of donors, and then you have to take the number of donors which still have the electrons in there. It's not ionized. So this ND is actually not ionized donors yet. You should say something like this. Okay. But we are concerned about the electrons in the conduction band. So actually, we care about the free carriers in the conduction band, which is this. So we have to deduce the number of electrons in the conduction band. Okay, ND minus ND is going to be 1 over G. That is the geometric vector which we are going to talk about in a minute. And e to the ED minus EF over KT plus 1. And we are going to have a Fermi level somewhere inside this flat band diagram. So we have a conduction band energy and valence band energy, and in the middle we are going to have a Fermi energy somewhere, and then we have a donor energy level if it is doped with the donors. And this one is going to be typically the geometric vector is 2, so that you can write down ED minus EF over KT plus 1. This geometric vector 2 is the common semiconductors usually show the geometric vector is 2. But in the silicon, which is the most popular semiconductors in the industry, the geometric vector is 4 for the silicon. So we often use the number 4 for the geometric vector in most of the cases, because we are going to use the silicon most of the time. All right? So we have 3 cases. The donor energy level is far away from the Fermi energy levels. Then ND over ND is going to go 0. And if donor energy level is much less than Fermi energies, then ND over ND approach to 1. Okay? And then if donor energy level is equal to the Fermi energy levels, then ND over ND, the ratio is going to be 2/3. There is the cases we can have. And we do the same thing for the acceptors. But let me mention about the acceptors. We're going to do the same thing as we did for the donors, but it has a different meanings in the acceptor case. Acceptors. Now, in acceptor case, you're going to have a conduction band and valence band, and everything is going to be referenced from the valence band. Okay, so if you set the Fermi energies, then it is the EF in the acceptor case is going to be the distance from the valence band. All right, and if you have a acceptor level somewhere, then that is EA, and then the distance is going to be EA, something like this. And the NA is a total density of acceptors, and Na, now that is the number of electrons at the acceptor levels, right? And these electrons come from the valence band, something like this, right? So this is called the acceptors, and the electrons should be supplied from the valence band, and then they're leaving holes in the valence band, and this holes is going to be a free carrier in this p-type semiconductors. So Na is a number of electrons at acceptor energy level, and that is equal to the number of holes, the free carriers in the p-type semiconductors. Free carriers in p-type semiconductor. So we are interested in this number, right? Na. Now, Na minus Na is going to be the unionized acceptors. That is the number of unionized acceptors. And Na minus Na over Na, the ratio is going to be 1 over 1/2 G e to the E F minus EA over KT plus 1, and that is 1 minus NA over NA. So in this case, we're going to do the same thing. And here, we're going to have 3 cases. In this case, like all acceptors are not ionized at the low temperature case, and then Na minus Na over Na is going to be 1, and then Fermi energy level is much far away from the acceptor level. All acceptors ionized. Then Na minus Na over Na is equal to 0, and Fermi energy is much greater than the acceptor level. So the acceptor energy is very close to the valence band, something like that, right? So let me give you the example of this. Before I give you the example of this, let me talk about the geometric vector a little bit. Geometric vector. G. That the geometric vector is most common semiconductors, you can set that the geometric factor is 2. But silicon, germanium, and gallium arsenide, which is most popular semiconductors, you're going to have electron spin effect. Spin effect gives you the G is equal to 2, and overlapping of valence band gives you G another 2, so that G is equal to 4 in most common semiconductors. Now let me give you the example of this. How do you actually do in the actual calculation? For example, let's say silicon is doped with phosphorus, okay? The amount of 10 to the 17th per cube. When you say it's 10 to the 17th number of phosphorus, 10 to the 17th per cube, if you think the silicon atoms density or the population of silicon atoms is 5 times the 10 to the 22. If you think 5 times the 10 to 22 atoms per cube of host metric, the silicon, this doping level is not that great. It's 1 millionth or something like that. Okay. So we're adding, when you say doping in a semiconductor, we mean very little amount of dopant should be doped. We're talking about a very little amount of a dopant. Okay? And then we just assume, first we assume that every dopant is fully ionized. Fully ionized ionization, which might not be correct, okay? We just assume that firstly, we fully ionization so that the number of electrons in the connection band is exactly the same number of phosphorus. All right? Then we can calculate the Fermi energies, EI, the intrinsic energy level, KT ln N over Ni, intrinsic carrier number. That when we have EF minus EC, if you measure the Fermi energy level from the conduction band, as we did in the class, then this equation is going to be NC, right? Effective density of states in the conduction band. Same token, you can write down the Fermi energy level referenced from the intrinsic energy level. Then you just change the effective density of states in the conduction band to the intrinsic free carrier numbers, electrons. And this EI and Ni is a function of temperature, and then it's a material constant. Material constant. So that we usually use the intrinsic energy level instead of a conduction band. okay? And then this EI is just half of the band gap, which is in a silicon case, or 0.55 electron volts in silicon. Okay, that is a material constant. So we use this equation most often times rather than these equations. So in here, what we are going to do is we assume that the full ionization of the system, so that we're going to put the number n to the 10 to the 17th per cube, and then we can find the Fermi energy levels in the system. All right? That's what we're going to do. And from that to Fermi energy level, we can get a number of free carriers again, so that we want to check whether this full ionization assumption is correct or not. So if you put that number, then EF minus EI is KT ln 10 to the 17th, 1.5 times 10 to the 10th, and that end up with 0.407 electron volts. And this means if you have a connection band and a valence band here, and then you have a donor level here, and then this, if you have instead of valence band here, we want to use the intrinsic energy levels, okay? And then the valence band is far from here. And then we set the Fermi energies in between, something like that. And then we just calculate this distance is going to be 0.407 electron volts here. The Fermi energies away from, referenced from the intrinsic energy level is turned out to be 0.407 if we assume that this phosphorus is fully ionized at room temperature. All right? And then we know this intrinsic level is from the conduction band, and this is 0.55 electron volts, as we mentioned here, okay? Then EF minus ED is going to be ED minus EF, and then that is 0.55 minus 0.044, which is going to be minus 0.407, and then that is going to be 0.099 electron volts. Okay, and this 0.044 is this phosphorus ionization energies. 0.044 electron volts is the ionization energy of phosphorus. Ionization energy of phosphorus. So this is the calculation that we have, and then from these values, we can calculate the electrons, number of electrons at the donor energy level. Okay? Number of electrons at ED. That is the probability ED of electron occupancy at the donor energy level is going to be 1 plus 1/2 e to the 0.099 divided by 0.4025. Okay? That is the room temperature KT value, and then that is 0.042. What does that mean? It means that this is the number of electrons to be sitting still at the donor energy level, not to be ionized. Okay? So the electrons occupying at the donor energy level, the probability is something like this, so that what you can set is 10 to the 17 times 1 minus 0.042. This is the number of electrons in the conduction band. This is the ionized phosphorus. All right? And then that is going to be 9.6 times 10 to the 16 per cube. Now, we assume that this number is going to be 10 to the 17th, but with this calculation, we can say we have a 4% error in the assumption. So what you are going to do is now, next step is, instead of a full ionization assumption, we are going to assume that some part of it less than 0.042 is going to be ionized. And then we do the same thing again, iteration, and then we end up with we can reduce the errors. Then we can find the exact values. But in most semiconductors, is full ionization is good enough. You just have a 4% error only. So we determine the fermion energy level in this way. Okay? How am I doing? Oops. Oh, what time is it? Oh, okay. Let's discuss about the N-type semiconductor. You can apply the same thing for the P-type semiconductors. N-type semiconductor means donors only. Donors only. And you can neglect the P-type, holes and everything. And in this case, the designation that we are going to use is the conduction band and the valence band. And we have a fermion energy level. And the distance is going to be EF, small f. And then donor energy level here and then the distance from here to here is going to be ED. All right? Now, the number of electrons is going to be the number of ionized donors. We assume they're fully ionization, whatever. The ionized donor is equal to the number of electrons in the connection band. That is the assumption that we are going to use. And then that is going to be ND minus ND. And then this thing is e to the minus EC minus EF over KT. And then that is ND minus ND over 1/2 e to the minus ED minus EF over KT plus 1. All right? And then that is ND 1 plus 2 e to the minus ED minus EF over KT. All right. And ED minus EF is equal to EC minus ED minus EC minus EF, and then that is EF minus ED. All right? And then NC e to the minus EF over KT is equal to ND over 1 e to the minus EF minus ED over KT. And then here we do let Z equal to the e to the minus EF over KT, and W is equal to the e to the minus ED minus KT. Then NC Z is equal to, how come this pen? ND over 1 plus 2Z over W, and NC Z plus 2NC over W G square minus ND is equal to 0. Okay, we just simply try to solve that equation, WND over 2NC is equal to 0. Z is now W over 4 plus W over 4 square root 1 plus 8 ND over NC W. So if we try to simplify the equations, let me write down then blue ink. Is this more clear? Can you see this better than this? now let's say ND over NCW is less than 1. Why don't you go to the office? Go to the office and find 2 more black pens. Let's say this thing is much less than 1, means it's a high temperature. Then this equation can be simplified to Z is going to be minus W over 4 plus W over 4 and 1 plus 4 ND over NCW. And then that is ND over NC. This means EF is KT ln NC over ND. Okay? So that is fully ionized. And in the second case, at low temperature, 8 ND over NCW is greater than 1, okay? Then Z now is equal to W over 4 plus W over 4, 1 plus 8 ND over NCW, and then that is 4W square root of 8ND over NCW, and then that is WND over 2NC. Okay? So EF in this case is going to be minus KT ln W ND over 2NC, and then that is 2 over KT ln to NC over ND minus ln W. So this EF Fermi energy level is going to be ln 2 and C over ND plus ED over KT. And then that is 2 ED plus KT over 2 ln 2 NC over ND. And at low temperature, Fermi energy level should be located in half of the donor energies. And from general expression for electrons It's going to be e to the minus ec minus ef over kt. We can set ec minus ef. It's going to be kt ln nc over n. Okay? So we can set n. In this case, it's going to be so kt nc over n is going to be ed over 2 plus 2 over kt ln 2 nc over nd. So ln nc over n is equal to ed over 2kt plus 1/2 ln 2nc over nd minus ed over 2kt is equal to ln nc over nd n over nc. Exponential ed over 2kt is equal to 2 over nd nc square root and n. So at low temperature, the electrons, number of electrons in the n-type semiconductor, it's going to be nd nc over 2 square root of that, and e to the minus ed over 2kt. This means n times some constant and temperature 3/4 is going to be exponential minus ed over 2kt. Okay, if you look at this, if you take a log, then you're going to have a straight line. And then we can determine the donor ionization energy levels this way. So C plus ln n times t to the minus 3/4 is going to be minus ed over 2k and 1 over t. This is different from the c there. And n is equal to nc mh star me star effective masses, and e to the minus ed over 2kt. And that means it is proportional to 3/2 and e to the minus ed over 2kt. Oh, no, that's, this is not a d. this is a band gap. And then here is the band gap. Okay, then and then n times t to the minus 3 halves is going to be to k and 1 over t. So if you plot at high temperature, if you plot ln n times t to the minus 3/4 here in the y-axis, and then x-axis is 1 over t. Then this is a high temperature, this is a low temperature, and at high temperature everything is ionized in the donor level, and then from intrinsic valence band the electron is going to excited to the conduction band at high temperature, so that the slope that we are going to have here is going to be related to the band gap. Okay? And at low temperature, we are going to have a slope related to the donor level, something like that. And in between, what's going to happen is that in between we're going to have a flat region. So let me draw a little bit more realistic. Okay? We're going to have a flat region here, and then we're going to have another slope which is different from this slope. So in between, we're going to have a flat region. As far as the free carriers are concerned, it's not the number of free carriers is not dependent on the temperature. There is some region for the temperature range. In this temperature range, we call full ionization. Now, physically, what we mean by this figure is that if you have flat band diagram, the conduction band and the valence band, and let's say this is a donor energy level, all right? We have a donors at low temperature here, and then as you elevate the temperature, then all the donors is going to be ionized to the conduction band, and then for the band gap here, we have a band gap energy here. Until we overcome the band gap energies by the thermal energy, the electrons is not going to be excited to the conduction band. And then the number of free carriers sitting at the conduction band is fixed to the number of free carriers which has been ionized from the donors for the temperature range in between here T1 and T2. And after the T1, then we begin to excite the electrons from the valence band. And then the electrons excited from the valence band can contribute to the total number of free carriers in the conduction band after we increase the temperature more than the T1, okay? In between, the electrons is not going to be excited and to the empty state to the conduction band And that is for the energy range corresponding to this much. In this much, in between these thermal energies, the number of free carriers in the conduction band is not going to be increased. So that's why it is fixed. But at the very low temperature to the T2 temperature, the number of free carriers is going to be is going to consist of electrons coming from the donor energy level, so that at that temperature, if you write down this is the temperature, then the Fermi energy is going to sit right here. Remember, the Fermi energy is nothing but the half occupancy of the electrons in the energy level. So if the electrons is coming from the donor energy levels at this low temperature, then Fermi energy should locate in between this half conduction band and the donor level, as far as the electron is coming from the donor energy level. And if you have free electrons coming from the valence band at high temperature, then Fermi energy should lie in between this band gap, half of the band gap, right? So in between this temperature, then Fermi energy is going to change something like this. So at very low temperature, very high temperature, the band gap of this semiconductor is going to move something like this. If you measure the Fermi energy level, then you see this kind of a change. And you see the Fermi energy as nothing but the electrochemical potential of the system. This is directly related to the electrochemical potential, and it drives everything, every reactions. Like a chemical reaction even, that has been driven by the slope of these energies. The energy, if you take a derivative of the energies, then it is related to the force, and the driving force, right? So realize that in a semiconductor, the Fermi energy can be changed with respect to temperature in this fashion. And so most of the semiconductor devices, you should keep the device in a low temperature. If it has a high temperature, then Fermi energy is going to be changed, and some kind of reactions can happen. Undesirable reaction can happen. Okay, if you have that, then we can extend this idea to the conductivity of the materials. In the semiconductor, what we can measure is the conductivity, right? As far as the electrical property is concerned. Now, conductivity is the important thing, and that is NQ mu, and then we have seen N is going to be changed with respect to temperature, something like that. And then mu, we have seen that the mu also can be changed with respect to temperature, mobility. It has a maximum temperature, it has a maximum mobility. Every material, semiconductor especially, has a temperature which can show the maximum mobility of the semiconductor. Right. At low temperature, and we distinguish at low temperature and a high temperature, sigma is going to be C to T to the 3/4, and then T to the 3/2, and then E to the minus ED over 2KT. Okay, the 3/4 come from the number of electron thing, and then 3/2 come from the mobility dependence on the temperature. Okay? That has to be multiplied like this, so that the total conductivity finally is going to be T to the 9 quarters and e to the minus ed over 2kt. Okay? So T minus 3 quarters is going to be C prime ed over 2k minus 1t. And let me save these figures. And at high temperature, still in extrinsic, but still in extrinsic case, then sigma is going to be C to the ND T to the minus 3 halves e to the minus ed over 2kt. And then sigma T to the 3 halves, it's going to be C prime ed minus 2k 1 over t. So this means if you plot ln conductivity T to the minus 9 quarters and 1 over t at low temperature range, then you're going to have a straight line, and then that is corresponding to the band gap over 2k. Oh, not the band gap, it's a donor level, right? But at high temperature, you have to change the y-axis like T to the 3 halves, and then you're going to have a straight line 1 over t that is corresponding to the minus eg over 2k. Here, you extrinsic range, you are going to have ed over 2k. That is the conductivity change with respect to temperature in the semiconductors. All right? Now, let me just talk about a little bit about compensation. Compensation means if you dope the semiconductor silicon with a p-type and n-type at the same time, what's going to happen? Then that means you have a silicon, something like that. Then what you are going to do is going to replace this thing and a p-type like a boron, so that one hole is connected to it. You can regard